Okay, everyone. I hope you're ready for our last keynote session of the conference. Last but not least, we have Diane Larlus from Naver Labs in Grenoble with us. I'm happy she joined. She's an expert on continual learning, but also on representation learning. And if I understand it from the title, this will be on the combination of these two worlds. So give her an applause, and then I give the word to you.
Can you hear me well? Yeah. So thank you very much for the introduction, Tine, and thanks a lot for the invitation. It gives me a very good reason to finally attend CoLLAs. This is the first time I attend this conference, and I'm having a great time. I think it's a great community, and I love all the discussions and the exchanges that have been happening for. Sorry? Is it better now? No? Okay, I will keep it closer. Then it's okay. So yeah, my point was that, well, I'm having a great time. I hope you're having a great time too. And you still have a bit of energy for what is coming next. And this is a very broad title, Lifelong Learning for Visual Representations. I have a very broad definition of what I think lifelong learning could be. And this is what I will try to show you this morning, also showing some of the recent work we've done along that lines in the team for the past few years. Okay, so let's start with the motivation and some definitions. So I'm sure all of you here, if you're here at this conference, you all came up with very good reasons to work on continual learning, right? Like that you're here for a reason. But I will give 3 possible answers to the motivation. Obviously, there's the biological inspired way that we've witnessed that the brain learns incrementally and is really good at retaining quiet skills. So we would like computers to be able to do the same. There's a very pragmatic reason for that. When you start tackling a new task, you probably don't want to start from scratch. You probably want to start with something you already have, a model that is already out there for a neighboring task, and you want to try to repurpose it for this task you now have to deal with, or maybe extend it if the old task is still relevant, as we will discuss. And this is one way to limit the compute by reusing, adapting, and transferring models from one task to another. This is an obvious direction for more ecological friendly AI. The last motivation I'd like to mention is really something that comes from the company I work for. So what you see here, you see 2 buildings. This is the headquarters of the company I work for, Naver. So this is the first headquarters that was there for a while. And then they decided recently to build a second building as a clone of the first one. But as a plot twist, the second building has been built from the start in order to welcome a fleet of robots in the building to be able to work seamlessly with humans. Oops, sorry. So the building has opened about 2 years ago. No, this is not playing. Sorry about that. Yes, now it's playing. So now you can see what the robots are doing. So they've been deployed and they're doing a bunch of simple tasks. So they're already delivering coffee, which is very important, right? And even if this task is very controlled, no matter how hard we plan, eventually these robots will run into something unexpected, an unknown object, unknown human behavior, unknown environment. So what I would like to argue is that at the very core of embodied applications, as soon as you want to deploy these embodied platforms and unknown environments, you will need this their perception system to be able to generalize and adapt to whatever comes. So this is, in my opinion, a very good motivation to work on lifelong learning. Let's go with a definition so we're all on the same page. I will say that lifelong learning is when you know that you won't be solving one task in isolation, but many, and you would like to make sure that when you train for one task, it's going to be useful later for another one, or more pragmatically, you would like to develop a set of tools so you can learn incrementally, retain acquired skills, reuse, recycle, or extend the skills. And there's very often a continual aspect to lifelong learning. So very often we call it continual learning. I tend to use both terms interchangeably, although I understood that I should pay attention with that and definitions are precise. But at any given point in such a sequence, you have a model for task A, and you would like to extend it to deal with task B. And there are two possible scenarios. Both are important, and we'll cover two different examples for each. So in the first option, task A is just a means to an end. You need task A to be simply better at task B. It's just a starting point. You don't care about task A anymore. And in the second case, task A is still relevant. And once you have your model, you want to adapt it to task B in a way that you don't forget too much. And in this case, you all know that the main challenge with this is the catastrophic forgetting challenge. So very often, continual learning is about classification, and you add incrementally a number of tasks, which can have new classes associated to it. And at the very end, you want to be able to recognize all these classes. But if we look closely at what can vary between this task A and this task B that we've seen before, obviously, you can have a variation across concepts. And this is very common in class incremental learning, open world learning, and novel class discovery, and many other scenarios. But as you all know, other things can vary, such as the image distribution, or also called the domains, in the domain adaptation and domain generalization literature, or you can have the task that varies. That's when you have a strong classifier and you want to adapt it for detection, for example. Okay, so maybe a few words about continual learning in the age of large pre-trained models, because, well, it started long before that, but I'm sure you know how ImageNet has fundamentally altered the field. You probably know the story, like how they used the WordNet ontology, an ontology handcrafted by linguists to select visual concepts and collect large data sets to associated to these visual concepts. So that's how they obtained what was considered extremely large at the time, 14 million images, covering more than 20,000 concepts. That was really unprecedented. And that was really a turning point in computer vision. And one of the outcome of this was obviously to allow convolutional neural networks to have enough data to train and give fantastic results. And it very quickly became common knowledge that the CNNs could be used off the shelf as feature extractor and would be an outstanding baseline for recognition. So this is an outstanding baseline in the own words of the authors themselves. So in this workshop paper, they took a number of benchmarks that everybody was using at the time. And they showed how the state of the art at the time, shown in green, would compare with simply using an AlexNet-like architecture used as a feature extractor and combined with an SVN. And this would lead to the results in red for each of the tasks. You can see by just using CNN as a feature extractor, combined with an SVM, you could have on par or better than state-of-the-art for many, many standard benchmarks. And of course, it quickly escalated after that. The data sets became larger and larger, and the models also larger and larger and more generic, and leading to the introduction of the term foundation model by Stanford researchers. In this presentation, I'll rather use large pre-trained model, and of course, not only impacting computer vision, but many other fields. So now in computer vision, it's extremely common to start from an existing pre-trained model that is generic enough, and then to simply transfer it to your task or to your tasks if you have multiple tasks and maybe a sequence of tasks. So in the rest of the presentation, I will assume two phases, a pre-training phase and a transfer phase. And we look at a few questions. We'll see how we can pre-train a good model, and in particular, how we can evaluate the generalization capabilities. We will also look at how we can train visual features with visual data, but also with data beyond images. And I will say a few words at the end about the transfer. Once we're done with the pre-trained model, how do we transfer to a specific task, or how do we use multiple pre-trained models? Okay, let's start with pre-training strong models. So what is a good pre-trained model? So let's start with a wish list. We would like this pre-trained model to have a broad knowledge of many things, many concepts, but not only. And if we go back to the generalization capability we would like to have this model to have, then if we look at the three angles that I mentioned, we would like this pre-trained model to be good uh, even in the presence of domain shift, task shift, and concept shift. And of course, because it's a starting point, it should be easily to adapt to new tasks that will come next. So if we go back to the definition of lifelong learning I gave before, you won't solve one task in isolation, but many, and you would like to make sure that training for one task will help for another. The other task is still unknown because we're doing pre-training here. So we don't know the target task. And this is what we're interested in. Now, as we've seen with the outstanding baseline paper in computer vision, researchers have very quickly found out that pre-training on ImageNet with its labels builds a model that allows you to extract visual features that are really good at other image classification tasks, but also other tasks such as detection, segmentation, and retrieval. So one way to see it is that ImageNet classification is simply a proxy task, a pretext to get good visual representations for something else. But now, assuming that you have an ImageNet size dataset with high quality labels for your domain of interest is quite a strong assumption. This is, for example, not true for medical images. So it would be nice to be able to reduce the annotation cost when you do this. And that's exactly what motivated self-supervised learning for pre-training visual models. So when fully supervised as a proxy task required fine-grained annotations and very often expert knowledge because not everyone can get these bird species or these coral types right. With self-supervised learning, you could just have some images for training. Now, because you have no annotation, how does it work? Well, self-supervised learning, I'm going to define it as an unsupervised set of techniques, but which borrow from the supervised tasks, except that the annotations, they're not provided by human annotators, but they're fabricated from the data itself. So we're solving a proxy task that is not necessarily an interesting task. It's not necessarily a task you care about, but this is just a way to build a representation that is going to be useful and hopefully capture what you need to do next. Many self-supervised learning methods have been proposed. One of the top ones that I will go back to later is DynoV2 that really shows extremely strong generalization properties. And again, that's kind of obvious, but to make sure we're all on the same page, as I said, this proxy task is not necessarily a useful task. Here you have the ROTNet method that asks the model to predict the right orientation among possible options for an image. This is a classification problem. This is supervised, but the label it has been automatically seen from the data itself. And then you take your encoder, use it as a visual extractor, and then you can combine it with a linear classifier to tackle another task such as leaf classification, but you can do many other things. You can like have smarter transfer. Now, these models, they're trained on some data, which obviously has an influence on how the model performs, and with a task that is not necessarily something that you care about. But still, you would like to make sure this is a good starting point. So you would like to make sure that your model generalizes. So let's look at that. As we said, ImageNet can be used as a proxy task with labels or without labels if you're doing self-supervised learning. And then you get a model that is supposed to extract very good visual representations. But how do you know these representations are good? Especially that you want to have the quality of the model without any other factor, right? Without knowing what the model will be applied to. So how do we evaluate the intrinsic quality of a model? And well, the way it's done in papers is that you go for as many tasks and data set as you can, and you test your model and you compare to competitors, hopefully with the same protocol. And that's already a very good idea for getting an intuition if your model is any good. But now, if we go back to the different dimensions that I mentioned before, what can vary between the proxy task that we use for pre-training and the target task that we will see later? Well, the concept can vary, the domain can vary, or the image distribution, if you will, can vary, or the task can vary. And while generalization across domains and across tasks have been studied quite a lot, there has been very little work on understanding how well these models generalize across concepts. So what I'm going to do next is walk you through an evaluation benchmark that allows to evaluate concept generalization. Okay, so the question we're looking at here is when training a model on a set of seen concepts, how well does this model generalize to new unseen concepts? So to give you an example, how do I train a cat classification model? Cat classifier, very important in computer vision, and you want to train it in a way that it will adapt faster and hopefully better to a new class such as caticons. The intuition behind is that the semantic similarity between the seen and the unseen concepts will play a role, because intuitively it should be easier to transfer to concepts that are more similar to your starting point. And this is what will guide the building of the benchmark. So first we need to define a semantic distance between concepts. So we need to define how close these two classes are. And the intuition is that a tiger cat is more related to European wildcat than a cabbage worm. And how do you do that? Well, we simply used the WordNet graph that, remember, is the one that guided the construction of the ImageNet dataset. And that is supposed to connect all the semantic labels. And we can simply use the lean similarity in this graph that will look at the closest parent. Now we have a way to rank a set of classes as the most similar from, to the least similar to a starting category. Now that we can do that at the class level, we can do that at the set level. So we're going to use semantic distance between sets of concepts. But now remember, what we want to do is to evaluate only concept generalization. So hopefully that's the only thing that should vary. So how do we make sure that the task doesn't vary? Easy, we will just use classification all the way. But we need to make sure that the image distribution doesn't vary. So for this, we are going to extract everything from the same data set, the very large ImageNet, the full one with the 14 million images and the 20,000 concepts. And from this data set, we are going to extract a set of 1,000 categories, which are the ones that are going to be seen by the models for pre-training. And if you know how this works, very often people do train on ImageNet 1,000 categories anyway, so this allows us to compare many models that are already pre-trained. Then we're going to extract different sets of 1,000 categories, which are increasingly distant from the 1,000 categories of the ImageNet challenge. Because we have all the images associated to these different categories, this allows us to define a training set, which is the only thing that the models are supposed to be exposed to at training. And then we have 5 test sets of increasing difficulty that I'm going to call concept generalization levels. And the idea is that it's going to be harder and harder to classify this, as we will verify. So we use this benchmark to evaluate a very large number of approaches. We looked at supervised methods, self-supervised methods, and a few others, such as weakly supervised. And we made a number of observations that I will not all details, but let's start with the first one. We've seen that it is indeed harder to generalize to semantic distance concept. As you can see, all the methods that have been considered, they have the accuracy that decreases as you go towards more challenging levels. And we made sure that the different sets have the same number of images and are equally balanced, so these numbers are meaningful. So this indeed verifies that it is harder to generalize to concept that's semantically distant. So this kind of grounds the rest of the study. We made other observations, and I would like to mention 2 of them. The first one is that the recent self-supervised approaches, they tend to generalize better. The second one is that label-based augmentation, you know, all these cut mix of strategies, they improve a lot for the scene classes, but it turns out that they hurt when it comes to concepts that are very different from the concept you've seen at train time. We have a few more of these observations and all the results that back up those in the corresponding reference. But what I would like to do now is to go back to what I think is the most interesting observation of that study. The fact that self-supervised approaches, they tend to generalize better to unseen concepts. And because they've been trained in a self-supervised way, of course, they're not as good on ImageNet classification as the supervised methods. And now I'd like to argue that a good model should shine both on the training task, but also on transfer. And they're good at transfer, but they're not so good at the training task. And that's, if we go back to the introduction, we're in the case where we think task A is still relevant. It would be nice to have this classifier for the 1000 classes. So we still care about task A and we would like to work well on both tasks. On top of this, it's a bit counterintuitive that access to more information, in this case labels, actually hurt generalization. At best, the model should learn to ignore that. So let's look a bit deeper into this and let me explain to you what you're looking at here. So in this one dimension, I'm going to report ImageNet accuracy. On this other dimension, I'm going to report a single transfer measure that is going to aggregate accuracy on multiple data sets, the 5 level of the COC benchmark, and 8 data sets that are very standard to evaluate transfer. How do we more concretely evaluate a model? A model is trained on ImageNet with or without labels, you choose. Then you use this model as a feature extractor, as is. You simply combine it with a linear classifier, one for the training task, one for each transfer task, and that's how you obtain the results. Okay, let's go back to these 2 dimensions and let's see how these different models behave. We see that supervised approaches, they're indeed pretty good at the training task, at ImageNet classification, but they're not so good at transfer. If we look at the top self-supervised learning and semi-supervised learning methods trained on ImageNet, Dino and Pose, they're much better at transfer, but this is at the expense of lower results on the training set, on the training task, sorry. So the state of the art is kind of defining a trade-off between these 2 aspects that are both important. And what we would like to do now is to find a way to train a model in a supervised way, so using labels. And we would like this model to still transfer very well without compromising too much on the training task accuracy. So now we've seen self-supervised learning methods, they're great at generalization. So what about borrowing things from what people do in self-supervised learning in order to train better supervised models as well? Well, if you have a model, something you can do is simply use the data augmentation that people use in self-supervised learning. So we could use multi-crop data augmentation. This is considering multiple crops of the image at multiple resolution. Something that is fairly standard in self-supervised learning as well is to use an expandable projector. So this is a way when you train for a proxy task that is not necessarily important to make sure that your model doesn't overfit to the proxy task. So the projector is used at train time and it is guarded afterwards and you simply use your model. And then on top of that, you can train class weights or you can simply replace them with class prototypes with the nearest class mean classifier introduced by Thomas Mensig and colleagues. So now let's go back to this 2-dimension graph I showed you, what is out there, and let's see how the different, the recipe I just showed you works in this case. And for different flavors of the recipe I just showed, we obtain models like this. And we see that some of them are better at transfer, some of them are better at the training task, and but they all improve on this trade-off. So we define a new envelope for what can be done between the training and the transfer task, and we decided to isolate 2 models. We have T-Rex that is even better than Dino at the transfer, but it's also still quite good at the train task. And we have TRX star that is even better than what was state of the art on the training task at the time, with a slightly better transfer performance. So my argument here is that if you still care about your training task and still want to generalize later, there's no reason for no supervision. If you have labels, you could use them. We've seen how multi-crop data augmentation helps. Something I didn't have time to go into the detail is the fact that you have a way to control how much you're good on the training task and how good you are on the transfer task. This is by playing with the architecture of the projector. If your projector is deeper, you will tend to be better at transfer, a bit lower at training task. Okay, so we've seen how we can pre-train visual representations and how we can evaluate how well they transfer. Now let's discuss alternative ways to train visual representations. So as we've seen, you can use ImageNet and its labels for pre-training, but we would still like to reduce the annotation cost. So we've looked at two things that are at the very end of the spectrum. You have fully supervised classification, you have self-supervised learning, and what happens in between? Well, very often images come with metadata, and I'd like to mention some early works that have looked at that. So you have Armand Joulin, who's worked on Flickr images using Flickr title, caption, and tags, and Dhruv Mahajan, who worked on Instagram images with the hashtags. And in both cases, what they did is use all this metadata, transform it into a discrete set of labels, and use that for pre-training. And this works really well. But text is more than that. So you can imagine also training with images together with caption information if you have access to such caption. And now I'd like to argue that caption supervision is weak annotations because it does not require expert knowledge. And on top of that, it can be mined automatically, sometimes from external sources. And let's see how we can use the full sentence and not transform a sentence into a discrete set of tags. Well, I'm sure you all know the mask language modeling task that has driven the good success of BERT. You have a sentence, you mask a token in the sentence, and now you would like to use the rest of the sentence to predict the mask token. And if you do that on many sentences on a large corpus, you get a very strong language model. What we have in our case is an image caption pair, but we can follow more or less the same idea, right? We can mask a token, and now we can use the rest of the caption and the image to predict the mask token. So in this example, we would like the model to be able to predict that what the little girl is holding is a red umbrella by looking at the image. Now that we've defined a proxy task, we need a way to solve it. So for this, we obviously need a visual representation. That is really what we're interested in. Remember, the rest is just a pretext. This is just a way to get better visual representation. At the end of the day, we will just keep this one. We also need a textual representation. It can be the one you like, maybe the one from the previous slide. You can use BERT pre-train. You can train it from scratch with the same proxy task. And you need a bunch of auxiliary modules that are going to combine these two representations in order to predict the mask token. And this is a proxy task that we called image condition mask language modeling that has driven two methods, ICMLM and VRTech. And and at the time, training on such data set allowed to be competitive with the top self-supervised learning methods trained on ImageNet. But this method would train on 10 times fewer images, just they had access to captions. I don't know if you know these data sets, but these are the MS COCO caption and the Flickr 30K. And these captions, they're really good because they've been written by human annotators who were asked to actually describe what's happening in the image. So small sets, 100,000, but high quality. Shortly after, the idea of training for image and caption was scaled to like much larger scale. And the clip method was proposed using a contrastive loss for training instead of this masked modeling task. And the main difference is mostly that instead of going for small, high quality captions, they went for extremely large but unfiltered image plus text. A data set that is not public, by the way. So these models like CLIP and all the ones that followed after, they're extremely good at generalizing to many things because they have seen many things. So it's a bit like you would have put the entire internet in a box and use that to create strong visual representations. And shortly after that, because we had access to these representations that could combine image and text and very powerful and very generic, the next step was to reuse these models and build on top of it to do text-to-image generation. So after Clipped, DALL-E was proposed, and you had all the DALL-E versions and all the stable diffusion versions. And now you have these tools that are available to us that if you provide a prompt, then you can get very high quality images. So you don't even need an actual cat to have cat pictures on the internet. So now I'm going to ask you a very provocative question. We have these black boxes. They provide images just by inputting text. Do we actually need images to train visual representations? This sounds silly, but why not? So what if we start from this slide that I've showed you over and over again, but instead of using images and labels from ImageNet, we remove the images, we just use the labels, or more precisely the label names, and we use tools such as Stable Diffusion to generate an entirely synthetic data set for training. So a clone of ImageNet, if you will. Well, in practice, that's extremely easy to do. You take Stable Diffusion, you give it a class name as input, and you get your synthetic image, so you can build sets for each class. And you can simply do it for all the ImageNet classes, such as Papillon, Lorikeet, and Pyrochip. And we did that, and the results were surprisingly good visually. But we noticed a few errors. I don't know if you see something wrong with these results. So the errors were mostly of 3 types. First, we noticed semantic errors. The Papillon class exists in ImageNet, but it refers to a dog breed, when Stable Diffusion has confused it with the word papillon, which is the French word for butterfly. We noticed a number of domain issues. So for example, the Pyrochip class is generating toy-like images or cartoony-like images. And more importantly, for most of the classes, we observed a striking lack of diversity in the set of images that were generated for each class. So we tried improving that, but we wanted to do it in a class agnostic way, some kind of recipe that would work for all the classes of ImageNet. We used the parent class in the word net hierarchy on top of the class name. We also combined the class name with the description. We tried generating the classes on random backgrounds, where the background have been randomly chosen from the places dataset. And then we also played with some of the Stable Diffusion parameters, such as the guidance scale, which is what controls how good looking the images are, how realistic they are. And we need a way to evaluate the quality of what we've generated. So to do that, we train a model on each clone of ImageNet obtained with each of these prompts. And we use this model to classify real images. And this is what we obtain. So this is on the ImageNet 100 for now, only a smaller set, but I will go to the large set later. So we see that these different steps of prompt engineering are indeed increasing the classification accuracy of real images. But where do we stand compared to a model trained on real images, a real ImageNet? And this is where we are. So we're not there yet. But let's look a bit more at what this model can achieve. So how do we evaluate the model? Of course, we can evaluate on ImageNet. And this is what I just showed. You can go from this to this red number here by doing some class agnostic prompt engineering. And then that's where you are compared to results on with a model trained on real images. But let's look at more dimensions. Let's look at multiple ImageNet flavors, because there are many different ImageNet flavors out there. So we have ImageNet v2, which is an independent test set, but similar property to ImageNet. We have ImageNet R and ImageNet Sketch that are different domains, but the same classes. And we have ImageNet A that is on purpose adversarial images. And in this scenario, we just train a model on synthetic images or on real images. And we use the classifier as is to classify real images. And this is where we stand. So we see that ImageNet and ImageNet v2 are kind of similar, but the gap reduces for different domains and even more for adversarial ones. Now there's another way we can use these synthetic models. It's for transfer. So transfer is a bit different. We use the model as a feature extractor, but then we still use real images to train a linear classifier on top. So we used the COG benchmark to evaluate concept generalization. So this is a benchmark I introduced just before. We used a number of small-scale data sets, and we used a long-tail data set. And now if we compare a model pre-trained on real images and a model pre-trained on this synthetic clone of ImageNet, we see that they perform on par when it comes to being used as a feature extractor. So to go back to this question that doesn't really make sense, but it was for the purpose of trying to see what we could achieve with these models, we've seen that we have promising results on the image invariance, but quite surprisingly strong transfer results. Obviously, this was just an experiment to try to understand what these models do, and this shouldn't be applied directly for any concrete application in transferred, because we still have to understand a lot more about the potential, but also the issues on the images that are generated by these black boxes. Okay, so now that we've pre-trained, what can we do? So very often in the application, at least I have in mind, you have this very large pre-trained model that is maybe with a very large architecture, and you want to use that to start tackling a very specific task where maybe you have constraints about the capacity of the model you can use. So maybe you would like to transfer to a smaller model, and one very convenient way to do that is to do it through distillation. So you're going to distill the large model into a small one by trying to learn from the output of the large one. And this is what Geoffrey Hinton and colleagues have proposed as distillation. Now, as I mentioned, we start having extremely powerful self-supervised learning methods out there that have trained on gigantic data set. So just to give you a small idea what Dino V2 is about. So Dino V2 is learning through self-distillation. It's doing mask patch prediction, but maybe more importantly, it's been trained on a curated data set at scale. So what the authors did is to have this 142 million images data set that is kind of clean and relevant for the computer vision benchmarks. So because we have now these new models, maybe we also need to study a bit more how we should do distillation with them. And that's what I'm going to talk about next. So how can we most effectively leverage those large models when it comes to training a smaller architecture for a specialized task? Okay, so one thing you can do is task agnostic distillation. In this case, you train your very large model on very large data set, or you get somebody else to do it for you and you use a pre-trained model. Then you can distill that model into a smaller student, ideally on the same data that the model has been trained on, and you just use this for initialization. And that's a fairly standard recipe for starting a smaller target task, such as a bird species classification, for example. You can also do task-specific distillation. In this case, you will train your student for two things. It will train for the task you're interested in using the standard task class with the provided training data and labels. And you will use the same data to also distill from the teacher in order to mimic the output of the teacher on these images. So you have these two different losses. And what should the teacher look like? What exactly should be this teacher? A standard strategy is to fine-tune the teacher for the task. So you take your teacher, you fine-tune it with a loss for the task, and that's a teacher you use. The problem is that it can be quite costly, especially if you have a very large architecture, and also it's not necessarily optimal, as we will see in the experiment. Something we propose to do instead is to go for something that is lighter weight. We would like simply to probe the teacher, right? So what does it mean? We keep the model as is. We simply add a small task head on top with one or two layers. We only train these parameters on the task, And this is the probe teacher that is going to be the teacher for the distillation. We did some experiments on very diverse sets of target tasks. We use classification in various domains, fine-grained classification and semantic segmentation. As a teacher, we use Dino v2, multiple architectures. As student, we try distilling in VITS or ResNet. And I will spare you the giant table of numbers, but among the observations that we've made that I think could be interesting is the fact that with such a teacher, such as Dino v2, probing the teacher is actually better than fine-tuning it for most of the scenarios we've tried. The probe teacher is weaker than the fine-tuned one if you just look at its accuracy on the target task. But when used as a teacher, it is still better to use the probed one instead of fine-tuned one, which I find interesting. We also show that task-specific distillation is complementary to task-agnostic distillation. They bring two different things to the model. And we've seen how drastic model size changes are possible through distillation in that way. Now there's one question we haven't tackled yet, because you're going to do distillation of this very large model for your specific task. So maybe you don't have enough data to distill from. So what can you do? And there, something you can think of is just what I showed before. We could use stable diffusion to synthesize new images to distill from. So if you want more cat images, that's easy. But the problem with that is it requires to know the class names, which is not always possible. And more importantly, it's limited to classification, or at least, in my opinion, it's not trivial to do it for other tasks, such as semantic segmentation. So what else can we do? Well, we tried using a tool that is called Image Mixer that is based on stable diffusion, but that is able to combine two images. So the advantage of this is it's class agnostic. You don't really need to be limited to classification, or it will work for any class you can think of. And you can even merge across classes. So if I have these two images here of a cat and a dog, and let me zoom in so you see better what happens. If I have image mixer on top, this is the kind of images we obtain. So we have this cat dogish image of this animal. And you can do it for other domains. You can combine, for example, a boat sketch with this octopus sketch and obtain whatever this is. So that's the final distillation pipeline. We have a student that trains from a probe teacher on top of the standard task, and the distillation is done not only on the images from the original set, but also on the set extended with synthetic images. And I don't know how, I don't have a watch actually because I don't see my notes. How long do I have? I'm good? Oh, brilliant. I was faster than planned. Okay, so then I will spend the time to describe what's going on. So again, no table of numbers, but I would like to show you the feature space, or at least the PCA projected feature space. I know there's a lot of information that is lost doing this, but if you look at the features that are produced by the teacher, in color, you see the different colors mean different bird species. In gray, you have the images that are obtained with the image mixer, so they don't necessarily have classes because you can merge across categories. And we see that the classes are pretty well clustered in that space. If you look at the student that is initialized, or the student after fine-tuning, it's not too clear how the classes are organized, but the feature space obtained after distillation lead to much cleaner clusters in that space. And now the last piece of work that I would like to show is what if there are several complementary pre-trained models to start from, and you don't know how to choose from that. Well, instead of having one pre-trained model and then transfer, we have something like that. We would like to merge multiple pre-trained models before having something to transfer from. And that's something you can achieve through multi-teacher distillation. But how should you do multi-teacher distillation, right? How do you merge multiple models into a unified pre-trained one? A fairly standard recipe for doing that is simply having your student being distilled from multiple teachers with multiple distillation losses that then you sum at the end. And because the features are not necessarily compatible with each other, you have a teacher-specific expandable projector. Remember, this projector is something that allows us not to have fit to the task and we can discard later in self-supervised learning. This is kind of a similar role here. Now we can improve this pipeline by doing some kind of feature standardization across teachers. Um, we may want to make sure that the information flows better. So not only distill at the last layer, but at intermediate layers as well. This is something that becomes possible if all your teachers and all your students have the same architecture. And finally, you would like to make sure that all the teachers contribute equally to the task. So we tried a few things, but what worked best for us was teacher dropping. So we're going to randomly drop a teacher during training, but we drop the teacher, we more often drop the teacher that has the smallest loss, so to let the other one learn. And this is how we obtain this universal model for classification, or unique, that I'm now going to evaluate. So in the experiments, I'm going to again show you a spider plot where we've looked at multiple dimensions. We've looked at how well the model performs on ImageNet and ImageNet v2. We're going to look at how well it performs in the presence of a domain shift using again ImageNet R and ImageNet Sketch. We're going to look at multiple transfer tasks, such as the concept generalization from COG that I introduced before, long-tail dataset, fine-grained datasets. And on top of that, we added two dense classification tasks, depth estimation and semantic segmentation. And so you can do that with the architecture that we're going to use. And for this, we simply use the protocol introduced by Dino v2, where you also do linear probing, but in a dense manner on top of your architecture. We considered 4 teachers, pretty strong ones, 2 self-supervised learning methods, Dino and iBot, and 2 supervised models, Day3 and dbot fine-tune. All of them have been trained on ImageNet, and we also use ImageNet for distillation. And for the evaluation that I'm going to show here, we use, well, all of them are based on this VIT-based architecture. We simply train a linear classifier on top. And this is how the teachers perform. So as you can see, they are quite complementary across the tasks. Some work better on some tasks and some are better on others. But now if we look at the distilled model that learns from the 4 teachers, we see that we have a model that is quite performing well at the multiple dimensions we're looking at. Especially, it's pretty good at transfer, and it's also pretty good at this dense prediction task used as a linear classification. Just to show you the absolute improvement between the best teacher for each task and the distilled model, you can see that it's at least on par or better than the best teacher on all these tasks. So for that part, we've seen how multi-teacher distillation is possible to have one strong pre-trained model starting from multiple existing ones. We've seen how a ladder projector and teacher dropping help in the scenario we've looked at here, and how this teacher is pretty strong at image level classification. As a conclusion, well, maybe a few ideas to bring home or to discuss later. In my opinion, lifelong learning is more relevant than ever, but its definition could be broadened. We've seen some example, but there's so many more out there that image and text are extremely relevant for each other. And beyond vision and language, we can imagine more modalities playing a strong role. And I'd like to argue that distillation is a very powerful tool. It's not as trivial as it looks, and it can go way beyond its definition. This is something that I've not covered in this presentation, but maybe you've seen how strong self-supervised or like weakly supervised models for 2D images have been successfully distilled in 3D models and are now helping a lot in geometry. So I think there's a lot there as well. And before concluding and taking questions, I would like to mention my amazing collaborators on the different projects that I discussed this morning. Most of the credit go to them. And very, very lucky to work with them. And yeah, that's it. And I don't know if you have questions.
Okay, we started a bit later, so we still have a bit time for questions. So, yeah.
Thank you for the interesting talk. When you were generating image with Stable Diffusion, what about the scale of the synthetic data set? In the sense that when you generate images, you can actually scale a lot the data set and use more images basically for free. So I imagine this has an impact on the results.
That's a very good question. So what I didn't mention is when we were building ImageNet clones, we generated exactly the same size. So for all the results I've shown, the original ImageNet training set and its synthetic clone, they had exactly the same size. But we tried having multiple, like more images. And I think we went up to tenfold, although it starts getting really costly to generate. So they were not exactly 10 times the same version. They were like some of the weaker one we tried along the way. And we could see that we slowly improved over like the one ImageNet clone, but we could never catch up, at least for classifying ImageNet images with the synthetic one. So yeah, we have this curve in the paper, and I'm sorry, I should have put it as a backup slide because it's a great question.
You started your talk with robots moving through environments, and I really like that in your office buildings. And then you switched to the ImageNet. If we sort of say, what would the transfer there look like? So if you went from ImageNet, which is basically pictures in the real world from people with cameras, taking pictures of things that they like, to the robots that are seeing things like dirty dishes and rubbish in office bins, which people normally don't take pictures of. What's the nature of that lifelong learning trajectory?
That's a very, very good point. Most of the motivation behind this work is driven by our research on embodied AI, but most of what I've shown is done on public benchmarks, so we can really evaluate them. And there's several answers to that. So first, it's good to be able to understand the mechanism at play on label data and where we can compare with others. So that makes sense. But even in robotics, it's not uncommon to start retrain on ImageNet and or even larger, because Dino V2 is now way beyond ImageNet in terms of scale. But maybe if you want to tackle robotics, it's a good idea to start from a very strong Dino V2-like model. And then you maybe want to have this one as your starting point for tackling the embodied AI applications, right? If you're going to do navigation or anything that is useful for a robot. So there's of course the distribution shift at play. And this is one of the things, one of the dimensions we evaluate when we see how well we generalize. We of course will have new concepts, which is another dimension we're looking at. And of course, we can get closer and closer as a starting point to the real distribution and data. So in that case, we could start doing the same thing with very long videos that would be recorded by these robots moving around, and this would be our training set, and we could have the same kind of pipeline. So for the pre-training, I think pretty much everything could apply and be done. And then for the transfer that I discussed, this is this gap that we have to deal with. I haven't covered at all how the robots, once deployed, could be incrementally learning. And that's extremely important. We're looking into this a bit, but it's not like mature enough for me to show result there.
Thanks a lot for the talk. I'm still my mind is still thinking about that plot you were showing on transfer versus accuracy. And I think when you first showed it, it made sense to me that there's this trade-off. Like in my mind, I'm wondering what you think about this. In my mind, if I have to separate, for instance, a lemon and a yuzu, I have to be like awfully specific on a very particular feature about this, which is hard to classify maybe in contrast to yuzu versus plum. But then in terms of reusability, obviously leverage way more features of the lemon for the yuzu maybe, right? I'm not sure if this intuition is correct. You can say your thoughts on this. So then when you were moving on the self-supervised kind of trajectory, and you're basically saying like, I can maximize both in a sense, right? I'm trying to wrap my head around this because in my head, like when things are extremely related, it actually becomes really hard to distinguish them, but maybe easier to transfer. So for me, there's this natural trade-off. I'm not sure it's so easy to maximize both of these things. Maybe you just have some thoughts on this.
That's really at the core of the work, right? So this is an excellent point, and we keep having the discussion. This is the discussion we had when we started this project. Like, we had a discussion whether we could, like, if there was a trade-off, if the student would be a trade-off of kind of being average of the student, or if we could do better than every student combined. And I was quite surprised that we had so good results actually for the teacher, because the fact that there's a trade-off is kind of intuitive. There's so much you can learn with a fixed budget of parameters in your model. So this we're just like, I will give you my intuition there, but some of my colleagues strongly disagree, so it's also fine, right? We keep having the discussion at this weekly meeting, but there's so much you can capture, and I believe that at some point it will saturate. But apparently these models are still powerful enough that this is okay to get the best out of all these 4 teachers and still be good at all the tasks together. So we haven't saturated yet in the sense of how because for all of this, we still train a linear classifier on top, right? So we just need to have a model that doesn't lose any of the information that will be needed, and it's easily accessible. I don't know, it's doing math with the hand, I'm sorry, but like that is easily accessible for the linear classifier to be captured. And somehow it works. We also have this plot, maybe that one I have as a backup slide. Let me check. Where we had the trade, like how much we use now. That I have the trade-off one on. Oh, sorry. So it's not there. Let me share again the screen. But so no, that's the backup one I had. That shows the trade-off, but when you project on 2 different dimensions only. But we have in the paper this analysis on how the weights are used, and where we try dropping more and more weights and see how much it degrades the results. And one observation is that the student degrades much, much faster than the teacher. So the intuition behind is that the teacher have more redundancy, and they're wasting a bit of how they store information, and the student seems to be smarter at having like storing as much information. I don't know if it makes sense. Like this is how we try to interpret this plot. I guess it kind of answers your question.
Thank you for your talk. I had a comment on the previous question and a question after that. So the comment is, I wonder whether we should look at accuracy versus transfer, or if we should look at robustness versus transfer. So my thinking is, if you'd look at like robustness to adversarial attack or even just noise in the data, you'd find that there is a trade-off. But when you look at it where the test set is fixed, like somehow you don't see that anymore. Just a hypothesis. I don't know if it's true, but I feel a lot more comfortable with that trade-off, if I'm honest. And then for the question, sorry, moving back
Can
to
I ask a question on your comments?
yes, yeah.
So when you said that you would evaluate robustness, with which dimension? Like you said, noise,
like adversarial attacks or things like that to see.
because okay, ImageNet A is adversarial attack, so that's one dimension that we're already looking at. But it's true that we haven't looked at the influence of noise.
But not the kind of like gradient-based attacks or anything like that, where you're trying to see like, okay, how easy is to attack this data within like an epsilon ball or things like that.
I see. That's your point.
Because I would imagine, so just to kind of, my hypothesis is that when you have the self-supervised, when you try to transfer, you need to preserve more of the variation of the data in the system so you can transfer. So that can make you easier to attack because now you're sensitive to all of these directions that are not necessarily useful for classification, but they will be useful when you do the transfer.
Mm.
So if you carry them around, then that should make you more vulnerable, if that makes sense.
Very
Um,
interesting thing to
So,
look
so
at.
that's at least my hypothesis. And sorry, I also had a question. So for the synthetic data part of the talk, have you thought about any form of reject sampling? So my thinking is if you just generate data, in some sense you can't do better than the generator, and the generator somehow is synthetic and it's not covering the real world. But if you add a step of reject sampling, like you can very quickly gain a lot from the synthetic data. And I don't know if you ever thought about that or like any mechanism like that.
So if I remember correctly, that's one of the things we played with to try to understand how it works. And this didn't survive the early weeks of the project. So I think it was, it means that we didn't come up with a suitable way to reject. It was not as trivial as we thought in the first place to be able to select the correct, well, the useful information or not. And I've shown some images generated for ImageNet, but I've not shown how visually the different prompts affect the appearance, and the best prompt are providing the most ugly images. Like it looks not anything like one of the classes we would like to recognize, in my opinion. Sometimes when you ask for an object in a background where the background makes no sense, the object disappears. You have weird things happening. But so the data set gets more and more noisy, and yet they get better and better at pre-training, which is, you know, something that was not directly obvious to me when we started the project.
Okay, we'll go for one more question in the back, and then we'll go for lunch.
Hello, great talk. Thanks for the great presentation. I have two quick questions. One is similar to something Razvan said about the robustness literature. So I've seen some similar plots there for accuracy on ImageNet, let's say, on one axis, and then accuracy on distribution shifts on the y-axis, and they sort of talk about these trade-offs. I thought it was pretty cool that you're showing this for transfer. I hadn't seen that version of it before. But I'm wondering if there's insights that we can draw from that part of the literature that would also work here. So if I remember seeing some papers that do this thing called model soup, which I have no idea why it works,
But
to
it
be
works,
honest.
right? That's crazy. It works.
Yeah, it's kind of
Why?
very, very surprising. But they have all these ways like greedy soups versus, I guess, other ways of doing it. And it's literally weight space averaging, I guess, of all these models. So have you tried similar ideas for this version of the problem?
So I don't think I know enough this literature about where they look at these two axes with ImageNet and this distribution shift. Happy to get more references about that, because I would be interested to see if we have similar conclusions of different ones, or if this could be one more angle to add to the study. And for the model soup, that works really well for some cases. That's crazy, but not as well for, at least for these different teachers that we combine it. Of course, distillation was much better, even the basic ones. But
Cool.
it's not fully clear to me how and why the combination works and what's happening during the distillation process. We have so much to understand beyond just showing that it improves results. Fully agree with that.
I know there's another question, so I'll ask you my other one later. Thank you.
Is there okay, but that's the very last one.
Sorry, I know you're hungry.
So I have a simple question. It's about the point that you mentioned about constant similarity. So if you you showed a white cat, a black cat, and a white rabbit, and the similar concept was white. What if you have a overlap between concepts, or if you have an image that have two concepts within the same image? So for example, you have a rabbit that is white, cat that is the black in a single image, and you showed it let's say an orange cat or something that overlaps, or can it create a bias, or I don't know.
So
Like
are you
that.
saying, are you asking if it's possible that we do have overlap in the benchmark I showed? Yeah, it does, obviously, because
Basically, what I wanted to know how that concept similarity works. So, for example, in this situation, if you have a white cat and black rabbit, and I show you a black cat, does it prefer the blackness, the color, or a shape? Basically, you said that WordNet, but I don't know how WordNet prefer the hierarchy. What is the similarity for?
so that's a very good. So there are two very good things to detangle, I think. The fact that indeed some images have multiple concepts, and it's just the way ImageNet has been built. The main concept is described, so we have to go with that. And I guess it's acceptable level of noise compared to the scale of the data set we've built. Now you ask, like, what happens if some of the concepts can co-occur? And the way WordNet has been used to build the ImageNet dataset, only visual entities have been used. And I don't think there are any attributes, or very few of them. So although there are multiple levels in the fine-grained hierarchies, like you may have cat, or like a parent of that, and multiple fine-grained classes, that we accounted for. So again, we did a lot more than just looking at 1,000 categories. We did a lot of cleaning before. We removed non-leaves. We removed parents. We made sure to minimize as much as possible what you just described. Of course, it could still occur, but we've tried to clean a bit the graph before selecting these concepts.
Because, you know, I'm asking because ImageNet has lots of issue in it. So, for example, you have an image of a toolbox, but it's labeled as just as hammer. It doesn't, it says that it's a tool, or you have a loss of label noise. I wanted to know how that works in concept similarity.
So label noise, there's nothing we can do about it. And the toolbox and hammer thing, hopefully it's clean with our filtering process, that we don't take parent class. If we made sure as much as possible to select carefully a subset of the ImageNet classes we could get our concepts from for the dataset to minimize this kind of impacts. But obviously, like a few of them must have slipped, because it's very difficult to review everything by hand. We tried, but yeah.
Thank you.
Okay, so we'll stop the discussion here. Let's thank Diane again.
Thank you.
So one more note, so we'll have lunch now. This afternoon there is the unconference session in good CoLLAs tradition. We start at 2 p.m. sharp here in this room.